Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture. This is general control valve analysis. It is very important, particularly with respect to electrohydraulic valves. The difference with the ordinary valves and electrohydraulic valves, or so to say servo control valves or proportional control valves, the spool or maybe poppet, everything, the ports, they are manufactured with very care, and they should have particular geometric configurations. And this general analysis is essential for analyzing even if an ordinary valve. Although we need not use such rigorous analysis, but this analysis will be helpful for general valve design as well as the most accurate type, say servo valve design. Now, first of all we shall develop general flow equations. We have considered 4-way spool valve. Some general performance characteristics of spool type valve useful for spool valve analysis in general are presented in this section. However, care must be taken in application of such general formula for a valve analysis, considering the valve's actual feature. Same analogy is also applicable to other type valves like flapper nozzle valve, etc. Now, look at this figure. What we see that this is 3-land 4-way spool valve. Look, if we look into the spool, it is having it is put inside a sleeve which again inside the valve body. Say this portion other than this spool, we can say this is a integral body, you can say inside the spool can move. This you may consider as a sleeve inside the valve. Now, here I would like to mention that we can directly put this spool inside the valve body, making a bore of this size and groove for the valve. But there are some problems. One of that is that machining may be difficult, as well this sleeve will worn out with the use of this valve, and if we use a separate sleeve, then we can replace that, whereas if we put this spool inside the valve body, we cannot replace it. So, due to various reasons, we use the spool which also can be accurately machined rather than if we machine the valve body for the bore. Now, in this spool, the larger diameter portion is called spool land. So, we have 3 lands in this spool, and look at this width may be different, may be same. Already you have seen that we need different width for land for different purpose. Then the middle portion, which is almost sometimes it is half of the diameter of the land, is called spool stem or rod. Now, these are the ports. Now, these port configuration, their width, land width, position of these ports with respect to other ports, and the land width and distance between two lands, all are very important and accurately manufactured for good performance of the valve. Now, we have already shown that in this body there is a supply of oil, which is PS is the supply pressure, and oil is going out, that is return, with a P0 the return pressure. On the other side of this sleeve, what is there? Two holes which are being connected to the load actuator. Now, if we look into this here actually I will show you another figure where we can understand that what may be the actual sleeve and the grooves. Now, here if we look into this, apparently this is the groove width, which must be equal to this also, may not be, this drawing may not be very accurate, but it will be equal. And what we see from this point to this point, they are having dimensions L1 and L2, and here L3 and L4. Later we will relate these distances for while we shall develop the equations. Now, these ports are also numbered as 1, 2, 3, 4. Okay. Now, this in the load side, what we find that we have used a QL is a flow, and here also the flow being returned is QL. The same flow has to be there. This is incompressible fluid. However, apparently we can say that what is the supply flow, that should be equal to Q, that should be the load flow, but they may not be equal due to the leakage. That is essential for the valve analysis. We should consider this. Now, as such the pressure is concerned, here what we find that PL is called load pressure. PL is called load pressure, which is nothing but P1 minus P2. Now, what is P1? P1 is the supply pressure to the actuator, and P2 is the return pressure from the actuator, whereas P2 is not equal to P0. Similarly, PS not equal to P1, because if these valves are used for control of flow or pressure, these orifices are such that there will be pressure drop, there has to be pressure drop. In fact, just for your knowledge, I would say if you look into a servo valve, in many cases you will find servo valve operates functions at the half of the pressure of the system pressure. So, suppose if you have you are using supply pressure 10 megapascals, you will find the valve actuator is being performed at about 5 megapascal pressure. So, so much pressure drop is there, so much power loss is there, but there is no other way. We have to compensate, we have to accept that for the performance, accurate performance, accurate control of the load motion. Now, 4 orifices of a 3 land 4-way spool valve we have shown in this figure, and these are completely analogous to 4 arms of a Wheatstone bridge. You must have knowledge about the Wheatstone bridge, which are used in electrical circuit analysis, and this looks like this. Here what I have shown, that Qs is the system flow, whereas written also Qs the system flow, then Q1, Q2, Q3, Q4 are the flow through 4 valves. Four valve ports, Q1, Q2, Q3, Q4, this will be Q4, this will be Q3 and this will be Q4, there is some mistake is there, and this is the load connection. Okay. And here the pressure difference Ps, which we have already mentioned, and here the respective pressure P1, P2, P3, P4s are there. Okay. Now, this analogy is often helpful in visualizing valve operations. Now, this here I have shown that valve displacement x v, and this is the positive direction. We have considered the positive direction along the direction of the force being used, force F1 being used to move the spool. Now, there is one confusion may be there. Usually neutral position is the position from where we consider the spool movement. Now, if it is the overlap valve, I have perhaps discussed sometimes that which is overlap. If the land width is more than this port width, then it will be overlap. Now, in case of overlap, usually you will find the middle position of land is matching with the middle position of the port. In that case, for the first movement, when the movement initiates, for small width, small movement, there is no flow in the valve, no flow. So, calculating this x v in the equations, what we are using in the equation, we have to take care of that overlapping portion. However, in this case, as if we have considered that this edge was matching with this edge, and from there we have started counting the x b, the spool movement. Okay. Let the spool is given a positive displacement along the direction from null or neutral position where x b is equal to 0. What is null position? That neutral position when from which valve can move either right direction or the left directions, that is called null positions. Now, usually we prefer to use the critical center valve. What the critical center valve means? This means that width of the land and width of the port is equal, but in fact the width of the land is slightly higher than the width of the port, because there is radial clearance. So, even if it is closing the port, there will be some leakage flow if both the width are same. To avoid that, slightly overlap is used. Okay. So, we have to take care of that overlapping portion while we are ultimately calculating the XV, the spool movement or orifice opening inside the equations which we are going to develop. Neglecting the compressibility flow at steady state. Now, what is compressibility flow? I have described that when within a controlled volume, within a trapped volume, the oil is pressurized, then there will be some motion of the fluid, that is called compressibility fluid, but compressibility flow, but that can be neglected for general purpose calculations. If we would like to more accurate calculation to find out the transient, then sometimes this compressibility flow is also considered. But in this case, to understand the main analysis, we have neglected that part. Now, what I have shown in this equation, that QL is called the load flow, it must be equal to Q1 minus Q4. Now, if we look into this, here this is the oil is going in the load side, and then this it is entering here. So, some flow will go this side. You may ask that why we have not considered the other side. Actually, this other side will be considered in other equations. Okay. If there is any flow, this movement is very small, it is in the order of 1 millimeter or even less in case of any valves. So, here this will be the much more important than this leakage. So, we consider Q1 minus Q4 is very close to the QL, neglecting this part. Okay. Similarly, QL, the same load flow which is being returned, we can write the Q3 minus Q2. Where QL is the flow through the load or simply load flow, and for which PL is the load pressure, which is expressed as PL is equal to P1 minus P2. Mind it, this P1 pressure will be inside here, that is equal to the one side of the actuator. Let us consider a linear actuator. So, one side of the piston, this pressure is P1, in other side of the piston pressure is P2. Now, in this case again we use normally that symmetric valve, that actuator, which means we have rod end at both ends of the piston. Normally for servo valves actuators, this is the both direction the rod end is there. So, area is same in both the directions. Okay. Normally it can be otherwise also, but it is normally like that. So, flow through valve orifices are described by the orifice equation, which we have already learned, but in this case these are as follows. Now, Q1 is equal to CD1 A1 2 by rho Ps minus P1. Look into this equation and the figure. So, Q1 is the flow through this orifice, okay, that is equal to coefficient of discharge at this orifice into this area, here the orifice area, This area I shall describe a little later. This area, not only this opening, we have to consider the width also, then we will find the area of this orifice, and then this is the system pressure, this is the P1 is the pressure here. So, we get this equation. Similarly, Q2 will be C D2 A2 2 by rho P s minus P2. In this case, again the A2 might be only the clearance area when it is in this form. So, this basically this will be a leakage flow, and Q3 is C D3 A3 2 by rho and P2, because P0 we may consider is equal to 0, or else it is like that. Suppose in this system here we have a pressure, let us consider 11 megapascal is the pressure. If you measure in a pressure transducer or simply a pressure gauge, suppose you have noticed it is 11 megapascals, and in the return side, as there are filters and other things, you may find that this is megapascal. So, what you would do, your P s should be that 11 minus 1 is equal to 10 megapascal, whereas P 0 is equal to 1 minus 1 is equal to 0. We first, while we are considering this pressure and this pressure, we first consider that. So, P 0 we put into 0, or P s is the differential pressure between these two. That is why equation is in this form. Similarly, Q4 also can be written in this form, and in above 4 equations, P is the system pressure, the drain pressure or outlet pressure P 0 is considered to be negligibly small in comparison to the other pressures. Although we have written in this form, but basically we should consider this P s is the differential pressure and P 0 is 0. Am I clear? Okay. Now, here another thing I would like to mention, that C D1, C D2, C D3, C D4, we have considered 4 different coefficient of discharge through A1, A2, A3, but it can be shown that such orifices for a valve is such that these all 4 coefficient of discharge are more or less equal, and in general a single value is considered for that. Okay. No orifice areas being now the orifice areas being the function of displacement x b. What it is? This area, basically that opening into the displacement will give the area of this orifice. So, what we write A1, the area which we have considered in the equation, is A1 x v, actually it is function of x v. Similarly, A2 is equal to A2 x v, A3 is equal to A3 x v, and A4 is equal to A4 x v. Okay. Now, I have shown here that what is x v and what is the spool motion as well. If you look into this, this is a full rectangular port. Look at this spool, here are the radial clearances, this diameter is the land diameter, this is the movement x v in this direction we have considered. Okay. Now, what will be this area of the orifice? This x v distance, this x v distance into the periphery, that means pi d. So, this must be function of x v. Now, how many equations we have developed? They are 7, and here actually we may consider in this, with this equation number there are 4. So, totally 11 equations are to be solved simultaneously to yield the load flow as a function of valve position and load pressure. Now, QL as well is the function of QL XV into PL, because this load flow that will definitely vary when XV varies, as well the load pressure will also vary. Now, this equation gives pressure flow curve. If we develop these equations, from there we will find the pressure flow curves, a steady state valve characteristics and the steady state valve characteristics. This means that here we should understand what the equations we have developed. These are, you have seen the root is there, etc. So, due to that these are highly nonlinear, and when you put into the dynamics it will be highly nonlinear, but at the vicinity of operating point, that means actually we would say that depending on the speed, suppose we are moving an actuator with a load and with a certain speed, that means we need a certain amount of flow. It might be the same flow again can be moved at a lower speed. Now, depending on that we will first open the orifice to the extent to have the desired flow. Okay. After that what we need to control that velocity. Suppose we need a constant velocity. In that case, say it has opened by 1 millimeter, then what we have to in control, what we have to find, that this spool we have to control about this 1 millimeter very accurately, so the flow is controlled to have the desired motion, desired velocity. What happens if the actuator moves with accelerations, then we have to decelerate this by just closing that one a little bit, and then again we have to open it. So, that sort of control is different issue of course, but our analysis, valve analysis will be at the vicinity of that flow, and at that zone we can linearize all such equations and we can solve. The theoretical analysis of QL considering all nonlinearities is very tedious, which I have mentioned. However, in the vast majority of cases the valve orifices are matched and symmetrical. This is another issue we should discuss. Now, what is called matched and symmetric? That is, two things are there, one is called matched and one is called symmetric. By equations, for matched orifice A1 is equal to A3, say this is A1 and this is A3. That means, when this spool will create this port area A1 and the port area A3, they must be equal. So, we have to take care in manufacturing, A1 should equal to A3 and A2 must be equal to A4. In this case, what is A2? A2 is nothing but this clearance, and it is a capillary passage, although it is orifice, it is a capillary passage, but this actually means if we move in the opposite directions, then for the same xv or minus xv, A2 must be equal to A4. So, that is the definition of matched orifice. Now, what is symmetric orifice? A1 xv and A2 minus xv, this what I have explained in the opposite directions, for whatever may be the value of xv, they will be equal. Do you understand? This is, you have to visualize this, what is meant by matched and what is meant by symmetric. Symmetric means is dependent on the spool motion, matched mean is a static condition, any general conditions. Okay. So, if these two are satisfied, then again we can many this what 11 equations we can minimize them. Actually, this if you look into the unknowns and the equations, these are sufficient, but handling 11 equations at a time will be difficult. So, we are trying to minimize those, and that is why it is preferred that for the control point of view also we make the ports are matched and symmetric. Then at null position A10 is equal to A20 and maybe A30 is equal to A40. All valves areas become a linear function of respective valve width. Now, this is slightly it looks like an unknown term. What is valve width? Here if you look into this, W is called valve width, which is nothing but pi d. This means that all these orifice area can be calculated by x b into the periphery of this valve land, which means this opening port is always a rectangle and that rectangle is having length is equal to pi d and width is equal to x v, okay, or x v minus the overlap portion, so to say. Now, this popularly called as area gradient. Now, in this case any orifice we call the area gradient. In this case, in this rectangular port we called area gradient is equal to constant is equal to pi d. So, to get an area opening, definitely this will be linear and that will be function of x v. Above expression is for full groove on sleeve, this pi d we have used, it is called full rectangular port or full rectangular orifice. Now, here I have shown that usually see this part is sleeve, this is put inside the valve body. What we find that in valve body there will be connection to the inlet, outlet, etc., pressure side, tank side, and at that position there will be hole. It might be only one hole is provided on the sleeve, whereas on the body there is again rectangular groove. So, that oil when is coming to that path that can go inside wherever may be the inlet or outlet. Do you understand this? Inside this we have a groove like this. Okay. Say due to this we have got this view, we have a groove and what we find there is small clearance, and while this valve is moving we consider this x b into that pi d is the area of the orifice and we call it full rectangular port. However, it may be partial also. How it is done and why it is needed? Now, here I have shown that partial rectangular port. What is the difference? I think you can recognize from this drawing, this is perfect engineering drawing. Here we have made a groove inside the sleeve. Let us consider this width and this width is also same. Okay. In this groove we have made, and this groove throughout the periphery of the inside sleeve. Instead of that, what is made that in that sleeve the holes are made. So, this is one through hole, this is another through cross hole you can say, and these are again made rectangular. Now, making a rectangular hole is difficult in a sleeve, but this is done. You will find that those who are manufacturing these valves, these holes are made. How it is made? Any idea? First of all, you can make a through drill hole and through which you can broach. You know this broaching tools, there will multiple tools will be there. Say from a circular hole, two rectangular hole. In the broach you will find initially you will find that maybe with a first broach is circular with a 4 corners diagonally opposite, it is cutting some material. Next will be slightly more cutting of the material, and finally you will find a square broach will pass through that, and that will make the hole. For 1 or 2 prototypes you can nowadays use the EDM technology to make that rectangular hole. Now, the question is that why we would go for such small rectangular hole in comparison to the groove. The reason is that this spool diameter, imagine this spool diameter, usually for very large flow 30-40 liters per minute, this diameter will be around 10 or 12 millimeter. Now, 12 millimeter into pi will be around 36 millimeter, and suppose you have given 0.5 x v is equal to 0.5. So, 36 to 0.5 about 18 millimeter square, is not it, 18 millimeter. That 18 millimeter square area is very large for controlling the flow. So, to reduce that we need to go for such small rectangular groove, so that flow is coming in through small opening. In that case clearly W will not be pi d, rather you can have, suppose this angle is say 20 degree. So, this will be 20 by 180 into d by 2. Okay. In that way we will get that each area, this each width, that into 4, say we have used 4, that might be, there might be 6 holes like that, 4 holes, 6 holes, it might be like that, and from there we can find out the W is equal to that much. However, we have considered A1 area. In that case, for the partial groove we will consider the number of holes into this width is the total width, and coefficient of discharge is more or less same in all cases. Okay. So, am I clear this part, that these are widely used in this control valves instead of this full port. In any case, with the linear displacement, variation in area is also linear. We need this linearity, that is why we should not go for any other configurations. If you look a little details, these corners are slightly rounded. So, when it is really opening at the beginning, slight variation in area also, I mean it is not linear, but that can be neglected, because at the beginning the pressure difference is high. So, it can be, maybe one can optimize that if there is a circular arc at the corner, what should be this circular arc for better performance, that can be done. But in reality there will be a circular arc, but that can be neglected for the practical calculation. Okay. Now, in case of servo valve, special care is taken in manufacturing to make valve ports matched and symmetric. I have explained what is symmetric, what is matched. Also, matched part assembly practice is adopted. What is matched part assembly? I have visited the moves control. They are very I mean they are pioneer in manufacturing servo valves. Now, what I observed, who are matching, who are assembling the sleeves and spool, in a tray they have taken at least 10 spool and 10 sleeves, and then in each sleeve they are putting their spool inside and they are measuring. They are manufactured in a batch, but for a sleeve they are putting 10 sleeves inside and measuring the distances. And after that I found that they are making a pair, then it might be out of the 10 sets they accept only 6 or 7, others they reject. Not reject mean not scrapped. These are again kept for another batch and then again they are matched. Then I asked that why it is done. Actually, in case of servo valve, this is so sensitive to this sleeve and spool dimensions that if there is slight error, the whole valve has to reject. In fact, the servo valve is like that, because servo valve means it is completely inside feedback control is there, no external control over there. So, this has to be very accurate. In case of proportional valves, it is not that you can externally control, but in case of servo valve it is not possible. So, the matched part assembly is most important there, just this is for your informations, but in reality we need, ideally we need matched and symmetric ports. Now, in case of matched and symmetric ports also Q1 is equal to Q3 and Q2 is equal to Q4, we can write this Q1 is equal to Q3 and Q2 is equal to Q4. Therefore, we can say this means the flows are equal in diagonally opposite arms in Western bridge. This is equal and this will be equal. Okay. Now, we consider equation 4, 6 and 10. So, we have considered these 3 equations and then we have put into Q1 is equal to Q3. Then what we get finally? We get PS, the system pressure is nothing but P1 plus P2. If you equate this, you will find that P1 is P2. Obviously, we have considered that coefficient of discharge, they are equal. So, they are cancelling, A1, A3 will also cancel. If we write like this equal to this, then squaring this 2 by rho, all such thing will go and we will ultimately get PS is equal to P1 plus 2. And similarly, equation 16 also from the other equation Q2 is equal to Q4, we will arrive into the same equation. So, from equation 3 and 17, these 2 equations we get to very important equation that P1 will be always equal to PS plus PL by 2. Now, here I would like to mention we have taken 4-way 3-land spool valve. These are matched and symmetric, and in that case what we find P1 is equal to PS plus PL by 2. That is why I told that if system pressure is 10 megapascal, other one will be half of that to get this value. You can equate like this. And P2 is equal to PS by PL by 2. They will be, I think these equations we have made a mistake, it is PS minus PL by 2. This will be minus. So, at no load P 1 will be is equal to P 2 is equal to P s by 2, because P L is equal to 0. Now, as the load is applied, pressure increases in one line and pressure decreases in other line. Okay. That is obvious, this is easy to understand that this has to be. Considering the flow, the following flow relations are obvious, that Q s is equal to Q 1 plus Q 2, Q s is equal to Q 1 plus Q 2 and Q s is equal to Q 3 plus Q 4. In summary, for a matched and symmetrical valve, equations 15, 16, 18 and 19 can be used, and equation 1 and 2 both becomes Q L is equal to C D A 1 by rho P s minus P L minus C D A 2 1 by rho P s plus P L. Now, you can look into this, we have used only one C D because we have assumed they will be same. Similarly, equations 20 and 21 can be derived as C D A 1 by rho P s minus P L plus C D A 2 1 by rho P s plus P L. You see, this is Q L is defined by this minus this, and Q s is defined by this plus this. Okay. Now, we will find some. So, we have only developed that what might be the relation of the flow pressure in a valve which can be used for linear control or not just on off control. The same spool you will find that is a 4 port 3 way valve, same spool can be used, but in that case we need not accurately maintain such the port configurations. In that case, just we make either full flow or it is 0 flow. We do not control the midway, but this analysis what we have present, that is for the controlling at the midway to controlling the orifice area, we are controlling the flow rate as well as pressure. Now, here to get the results, how much force is required, what will be the transient etc., we should use some more useful coefficients. What are these? First of all, pressure flow curve to be linearized at the vicinity of an operating zone. So, we have shown that the pressure flow curves which is equal to Q L is equal to Q L is a function of x v and P L, that equations. So, we now expand that equations and we will find that how it can be solved. Now, this will help in predicting the dynamics at this same operating zone. I have explained that we cannot analyze this valve for all operating conditions. We have to consider a particular operating point, and at the vicinity of that we have solved the equations. Now, in real control what is done, depending on the position of the valve, these parameters are calculated, and that is, say for example, we are using a proportional control valve. With respect to that, either there will be chart from experimental data or theoretical data, from there at a particular position what are the parameters that we will take into account, and then there will be the computer calculations. It might be very fast because of the linearity in the equations, and then that will be given to the feedback. In case of servo valve, these are automatically done in the electronic devices put inside, or maybe some other mechanical devices also. Now, considering equation 4.12.9, that this is the, as I told, that this is pressure flow equation, and expanding, we shall now expand in Taylor series at an operating point where let us consider the initial desired flow is Q L I L 1. Then Q L is equal to Q L 1 plus del Q L del x v del delta x v plus del Q L del P L plus delta P L plus then there will be del square Q L del x square etcetera etcetera, Taylor series as you know, but in reality the second order terms will be negligibly small. So, that part we can neglect. So, therefore, for that particular operating zone where we need a flow of Q L 1, and after that this will be Q L 1 plus something minus something for that operating zone. Okay. What we can write for that operating zone? We can write Q L minus Q L 1 is equal to delta Q L, that is the difference, is equal to this part, and we have neglected other part. So, the equation 4.12, this is 24, is very useful in valve analysis. In fact, we should remember this equation. Now, equation 24 is the valve characteristics equation where we define two derivative terms as follows. These are very important. We all the fluid power control engineer, they will say what is flow gain? Flow gain is equal to K Q is equal to del Q L del x v. What we are looking into that equations, equation 24. And another term, the direct unique term, is that flow pressure coefficient, that is K C is equivalent to minus del Q L del P L. Okay. So, two components, two coefficients, flow gain and flow pressure coefficient. You should remember this. Here interestingly this is having minus sign. Why minus sign is there? We shall examine later that del Q L del P L is always negative. What does it mean? We have put this minus sign so that K C is always positive, because we will use this positive term in further equations. But why this is negative? Why this term will be always negative? Because if pressure increases, flow decreases. So, this are a reverse function, that is why always a minus term will come, negative term will be here. So, this negative with this real negative value, if you put it there, K C will be always positive. Now, another term, this is also we use in electrohydraulic valve analysis where we accurate control is required, which is called pressure sensitivity. But this pressure sensitivity is actually derived term from that two derivatives. Okay. So, how this is you can see clearly if you have look into the other equations, this can be derived as del P L del x v is equal to flow gain by flow pressure coefficient is equal to this, and finally, we would say K P is equal to K Q by K C. Here as this valve this value will be positive. So, we are considering only the positive sense, do not confuse with this. Here no negative sign is there, because already after you are calculating these you will find this value. Now, these three values are normally provided by the manufacturer. So, if you use a valve, you will find this are 3 coefficients are mentioned there, or else you can also calculate if you get the data. With the preceding defined characteristics of the valve, the pressure flow curve becomes in linearized form as del QL is equal to KQ del XV plus KC del PL, that this is the flow gain and pressure sensitivity. In this term we can write down the equation. That means, if these two values are known for a valve, if the valve characteristics are fully defined in a operating zone, that means, for each and every operating zone you should have these values available in your hand, and then you know what will be the displacement, and this pressure you can measure or pressure you can calculate to have the load flow. Now, once this is calculated, then our actual interest will be this one. If we can give this much displacement, then automatically this will be adjusted. So, this is the control feature of this spool valves. Now, you see this actual equations are nonlinear and complicated, but we have arrived into the simple form, and if these two characteristics, these two coefficients are known, then we can do it. But in normally when we go for selecting the valve, what we should look into. So, this is applicable to any valve analysis. In case of flapper valve, of course, their orifices are different, their gradient, area gradient will be different, but still this analogy will be applicable to that. Flapper valve will come sometimes later, but spool valve we are now we are analyzing. These 3 coefficients are called as valve coefficients and are extremely important in determining stability, frequency response and other dynamic characteristics of a control valve. Okay. It is to be noted that flow gain directly affects the open loop gain and thereby stability. That means, flow gain is directly controlling the stability of the valve, whereas flow pressure coefficient directly affects the damping ratio. The pressure sensitivity accounts for the ability to break away large frictional load with little error. So, we shall look into all these values while we are selecting a valve. The values of the valve coefficients depend on the valve operating point that I have mentioned. This will vary to different point. The most important operating point is the origin of the pressure flow curves. Why it is most important? Usually what we need, that a load has to be made in one direction and next moment it has to move in the other directions also. So, definitely operating point near the null point is most important. Okay. So, we analyze for that point and we should call that this I have already explained, because the system operation usually occurs near this region, and at that region the valve flow gain is largest, giving a high system gain, and the flow pressure coefficient is smallest, giving a low damping ratio. We need high damping ratio actually, but at that zone it will be there. But hence, from stability point of view, this operating point is critical. Importantly, a system which is stable at that regions remains stable and quiet at all other operating points. So, if we analyze a valve for that region, if you find that performance is good, we can consider at the other points for larger flow in the same direction, right direction or left directions, it will be stable. The valve coefficients evaluated at the operating point are called the null valve coefficients. You see, this null position actually may be the neutral and 0 positions, but when we are considering a particular operating zone, then for ideal position for that amount of flow, say QL1, say 30 liter per minute, we will say that XB position is the null point, and about that point the coefficients are called the null valve coefficients. Okay. So, general flow equations and linear analysis valve coefficients in summary, you can say the matched and symmetrical port, this is the load flow and this is the system flow. If you, if possible, try to remember these equations, and the valve coefficients are, this is the flow gain, this is the flow pressure coefficient, and this is the pressure sensitivity, and expression for pressure flow curves become in linear form as del QL is equal to KQ del XV into KC del PL. Okay. This is the flow gain and this is the pressure flow pressure coefficient. Okay. And with this I end today's lecture, and I have followed mainly the hydraulic control system, the book hydraulic control system by merit, and however, some knowledge of the orifice and others have more detailed in Martin and McLeod. So, I suggest the to read this book. Thank you.